Hello all and welcome to this lecture on concepts of thermodynamics. In today's lecture, we will solve a problem by the aid of a computer which you might have already solved by hand, that is by using a table. So I have launched TES and I will open a new file. Just the font size. Problem is as follows. Water vapor initially at 3 megapascal and 300 degrees Celsius is contained in a piston cylinder arrangement. The water is cooled at constant volume until the temperature reaches 200 degrees Celsius, which is state 2. Water is compressed isothermally to a state 3 where the pressure is 2.5 megapascal. The task is to locate states 1, 2 and 3 on the TV and the PV diagram. And we must determine the specific volume at states 1, 2 and 3 and the quality at state 2. So, before proceeding, it is worthwhile to quickly see the property plot for steam, so that we can make a nice estimate. So, we go to plots, property plots, we go to steam, and we draw P or TV let's draw a TV diagram and let us include the line of 3 megapascal. So, 3 megapascal in kilopascal is 3000. So, we go to plot, property plot, and we have to switch off the isentropy lines and constant quality lines. We just want to see the 3 megapascal line in a TV diagram. So, this is the diagram. So, we have the condition where it is 3 megapascal and 300 degrees Celsius. So, it is 3 megapascal and 300 degrees Celsius. So, if you look into this figure, 300 degrees Celsius is this line and it intersects the 3 megapascal line over here. So, the state 1 is superheated vapor, then it is cooled to 200 degrees Celsius in an isochoric manner. Okay. State 2 is 200 degrees Celsius and V2, the specific volume, is equal to V1, because there is no escape of mass. So, in a piston cylinder arrangement, the mass is fixed, and so because the total volume remains constant between states 1 and 2, the specific volume is also constant. So, that is the logic we will use. So, if the total mass is constant and the specific and the total volume is constant, then obviously specific volumes are equal, thus V2 equal to V1. So, then from this particular point over here, the line will move along this axis because it is a constant volume process. So, we expect that the process will look something which is a vertical line. It will go up until it hits the 200 degrees Celsius line. So, we will reach a point which we expect to be in the two phase region, in the saturated dome. After this, it is compressed isothermally to a pressure of 2.5 megapascal. So, it will move along an isotherm. So, it will move along this line up until it reaches the 2.5 megapascal line. So, if we draw it by hand, so this is the 3 megapascal line over here, let us draw it in blue. So, this is T and this is V. So, quite naturally the 2.5 megapascal will be at a lower point, because we have already seen that T sat and P sat are monotonous and linearly increasing. So, this is 2.5. I have exaggerated how this looks. So, it starts somewhere over here, okay, and then it goes down iso. So, actually we need to know what the pressures are, but anyway maybe it goes below 2.5. So, state 1 is like this, state 2 is like this, and then it goes in a isothermal manner until it reaches maybe this 2.5. Okay, this is how maybe it looks like. So, the exact nature we will see, but it is good to have a physical picture before attempting the problem. So, that can be easily done if you have a look into the property plot. So, let us proceed. So, state 1 is P equal to, so let us define it inside an array, so that it will be convenient for us to plot. P1 equal to 300, 3000, okay. This is in kilopascal, because we recall the units over here that the pressure is in kilopascal. If we choose the pressure to be megapascal, we can directly write here 3, but right now it stands at 3000 kilopascal, and the temperature is given as 300 degrees Celsius. Now, state 2 is simply T2 is given to us as 200 degrees Celsius, and the only other information that we know is V at 2 is equal to V at 1. Nothing but saying that the specific volume at 2 is equal to the specific volume at 1, and thus we need to actually determine the specific volume at 1, and thus V1 equal to volume or steam T equal to T1 and P equal to P1. I repeat again that the function volume requires as an input the working fluid, and then a command of the form T equal to something, comma P equal to something. I mean, you need two independent properties to be fed to this function. In this case it is T and P, it could be quality and something, but here it is superheated, so we can use directly T and P. So, T equal to something, I could have directly written here 300, but it is a good programming practice to write here the variable and declare the variable somewhere else, so that you do not have to repeat it again and again. Okay. So, volume steam T equal to T1 and P equal to P1. So, this gives us the volume at state 1, and with the help of this we have obtained the volume at state 2. State 3 is such that it is a isothermal process, and thus T at 3 will be equal to T at 2, and we know that it is isothermally compressed to a pressure of 2.5 megapascal. Isothermally compressed to a pressure of 2.5 megapascal. Okay. So, thus P3 is equal to 2500. So, let us see, if we run this, we have obtained all the various quantities. In order to plot state points 1, 2 and 3 on the PV and the TV diagram, we need to know the volumes and the pressures at all the 3 points. So, let us evaluate the pressure at state 2. So, clearly in this case we have two independent quantities which are T and V, and thus in order to obtain the pressure we recall that we need two independent quantities which are temperature and volume in this case. I mean, we will see later on that there can be any other quantities, but they need to be two independent quantities. Okay. In the dome, for example, you cannot make use of temperature and pressure to find out other properties, because temperature and pressure are related, they are not independent. Okay. We have already seen this. correspondingly V3 equal to volume, steam, T equal to T3 and P equal to P3. So, if we solve this, okay, so thus we have obtained that the pressure is 1,555 for the state point 2. So, naturally this point is at 1.55 megapascal as we suspected. So, this line is 2.5 megapascal, this line is 3 megapascal. So, there is a line like this, like this, which is 1.555 megapascal, and the point 1 goes first to this lower pressure, upon which when you cool it, when you are compressing it, see you are compressing the fluid from state point 2 to 3. Process 2 to 3 is isothermal compression, and P2 we have just found out is 1.555 megapascal. So, when you compress something, it is only natural that the pressure will increase. So, you obtain P3 which is larger than P2. So, here P3 was given to us as 2.5 megapascal, and thus P2 had to be lower than 2.5 megapascal, and thus we already, without even actually getting the values, we could estimate that yes, it would start somewhere at point 1, then it would go merrily to some pressure which is lower than 2.5 megapascal, then when it is compressed, it reaches the 2.5 megapascal line, alright. And the fact that the specific volume has suddenly increased, okay. See, the specific volume has suddenly decreased. It was 0.08, 0.08 and 0.001. So, we recall that the density of water is somewhere around 1000. So, specific volume is 1 by density. So, that implies this is in the subcooled region. So, the specific volume does indicate that point 3 is in subcooled liquid, which we have already guessed because point 2 was at 1.555. If we fix the temperature, we cannot go to a higher pressure unless we go to a subcooled region. So, up until we compress till the edge of the dome, so the edge of the dome is here, till this point the pressure also remains constant, because we know that in the dome so suppose this line is 1.555 and this line is 2.5. We started somewhere over here. We know that as long as I remain inside the two-phase dome, or the saturated dome, if process is, so this is the T axis, this is the V axis. If the process remains isothermal, then inside the dome it is also isobaric. And if at constant temperature you now increase, if at constant temperature, if you keep reducing the volume, you now start going into higher pressures, because you are travelling like this, because the temperature is constant, you have to go in a horizontal manner, and then you start going from a pressure of 1.555 to something higher than that, and then eventually you hit something which is at a higher pressure. You hit the 2.5 megapascal line. So, this is how that compression leads to an increase in pressure. If there was no increase in pressure and it was in the compressed, and if it is compressed, then it will indicate that you are still in the two-phase zone. So, for example, if the compression was done up until this point, if the compression was isothermal and if it is done up until this point, then you would see no change in the pressure, because you are still in the two phase region. In two phase region, the temperature and pressure are locked, which is to say, given a certain temperature, you know what that pressure is, and we have already seen that this is called as the saturation temperature and saturation pressure. Okay. So, enough of schematics, let us see actually how we can plot using EES. Okay. So, try to follow the logic. So, let us go to plots, let us draw the property plot of steam on the TS and let us include certain lines. Let us include the 3 megapascal line, let us include the 2.5 megapascal line, and let us include the 1000 this line. So, this is the plot that we obtain. Let us rescale it for our convenience. So, we do not need the axis to be so large. The maximum goes to maybe 0.2 on the x. The y axis maybe we can have from something like 180 and it can go to a maximum of maybe 350. So, these are the 3 isobars. This is the lowest isobar, this is the middle isobar, and this is the other isobar. Let us have some space on the left hand side also. That's too much space. Oh, sorry. Okay, like this. So, now let us go to plots, overlay plot, because we now want to overlay our points onto this property plot, and we have T and V. So, on the x axis it is V, on the y axis it is T. Let us draw them as filled squares. So, this is how it looks like. Okay. So, here it is just outside. Okay. The 2.5 megapascal line has a very sharp slope on the supercooled region. Whatever I have shown here, it is a schematic, but in reality it has a very sharp slope. The meaning of the sharp slope will be clearer in the later classes. It just means that for a liquid, del T del V is very large. Okay. So, it almost goes like this, and thus you do not need to travel so far, you already reach this point. Okay. And that is why it looks almost like it is on the edge. In reality, it is outside the edge. Okay. So, this is the way the process goes. We have started from 1 like here, and we go to 2 at a lower pressure, and then we go to this. So, this is how the plot looks, state point 1, 2 and 3. Alright. So, we have been also asked to plot the PV diagram, plot the state points in the PV diagram. So, let us go to plots, property plot, steam, PV, and let us include temperatures of 200 and 300, that is all we require. So, let us change the limits. On the y axis we can make do with a pressure above 1000, not even 1000, 1200 maybe, and we do not need to go so high, we are happy with 3500. On the x axis we are happy with the minimum, but the maximum maybe it needs to go to 0.2. maybe let's take it as 10. So, on this plot, let us superpose the points. Overlay plot. On the x axis, we have volume, on the y axis, we have the pressure. So, one moment. So, this is obviously wrong. The process actually does not happen like this. Okay. So, what is the correct way to do it? So, this is the 200 degree Celsius line, this is the 300 degree Celsius line. It went from 300 degree Celsius to 200 degree Celsius in a isochoric manner, and then something wrong has happened. But why? Obviously, we are not shifting like this. Let me try to justify by drawing another schematic. On a PV diagram, the isobars, the isotherms look something like this. This is 300 degree Celsius, this is 200 degree Celsius. So, we start off at a point over here, this is point 1, we end up on a point over here which is point 2, and then process 2 to 3 is isothermal compression. So, if it is isothermal compression, it has to follow this particular line. Okay. And because it is compression, it has to go in this direction, because during compression the volume has to reduce. So, up until the point it reaches this point, let us call it as 2A, there is no change in pressure, because once again I reiterate, we are in the saturated dome. From point 2 to 2A, any change in the volume does not happen with a change in pressure. If the temperature is fixed, the pressure will also be fixed. After this point, you compress isothermally, you start going on this line. The reason being, this is how the isotherm looks. This is the same isotherm. This is 200 degree Celsius isotherm. So, the final point lies somewhere over here, and this corresponds to 2.5 megapascal. So, this point over here, this is actually 2.5 megapascal. But what has happened is, the computer sees 3 points, 1, 2 and 3, and it simply joins them by a straight line. So, this is where we have to understand that merely giving the computer values is not sufficient. In order to understand actually what is going on, one must understand in a schematic manner what is the process which is going on. Okay? So, in order to actually have a true understanding of this process, if we want to really plot the process, what should we do? We have to obtain point 2A. Okay. We have to actually obtain point 2A. So, then let us do it for completeness. So, this becomes our state 4. It is just for our understanding. Okay. So, T3 is isothermal. So, this point I am calling as 3 now, and that is isothermal. Okay. So, because it is lying on the isotherm. So, now how else can I quantify that point? I know the temperature. What kind of property do I need? Do I know the volume? No, I do not know the volume. I cannot guess the volume. What is the other property that we can use over here? If you said it's the quality, you are correct, because we have already seen that in the saturated dome, it is the quality and some other property that we can use to quantify. So, x equal to 0 is a point on the left limb of the saturated dome. This x, so we can directly find V3 equal to volume, steam, T equal to T3 and x equal to 0. Similarly, P3 will be pressure, steam, T equal to T3 and x equal to 0, just for completeness. Let us now do the plot. So, we have already done the plot. So, let us go here and remove, so let us go to plots, overlay plot, and on the x axis we have volume and on the y axis we have pressure. Okay, let us do it by a red line and filled diamond markers maybe. Oops. Oh, we have to first compile the program. Oh, sorry. You have to first run the program so that all the variables are now in the memory. And now we go to plots, property plot. I mean, it opens up a new plot, but we can make use of the old plot. So, here we have to first remove the old plot. We will remove the old plot. I have just double clicked on the figure and we get all the components of the figure. I have removed the old plot and now I can go to plot, overlay plot. On the x axis we have the volume, on the y axis we have the pressure, and let us join it as this. There you go. So, this is how the process looks like. This is state point 1. Let me increase the marker size. This is point 1, this is point 2, this is point 3, this is point 4. So, this is how we go from point 1 to 2, and then the isothermal process actually takes it to first a saturated liquid and then a subcooled liquid. And in the process of compression, the pressure increases. Even in the TV diagram, we will see another point appearing just at the boundary. So, plot, overlay plot, on the x axis we have the volume, on the y axis we have the temperature. So, there is a point just on the edge. If we zoom in, we can see. So, here you go. I mean, these are all numerical artifacts, but this point is on this line, is x equal to 0, and this point is in the subcooled liquid. Okay. So, this is how you do it. And I hope by means of this example, you are convinced that one should always have a physical feel of the problem before attempting it, because that way you know where something is going wrong, or whenever you are doing something which is maybe not physically realistic. Like we saw, the plot drew a straight line from state point 2 to 3. It was not a physically realistic thing, because isotherms do not behave that way. So, you should have an idea of how P and V vary for an isotherm, and in a TV diagram how a isobar looks like. So, just play around with the software, have a look into the property plots, plot different isotherms, plot different isobars, and I will see you next time with another example. All right, thank you.